Are we ready? You have the words in front of you, right?
Yeah.
I've had a total in my 30 years of teaching chemistry. I've been teaching for 46, but 30 years of teaching chemistry. I've had six total students memorize that song and sing in front of the class. All right? That is something to think about if you would like to get some extra credit.
Oh, I'm so down.
Are you ready? All right, here we go. Here's the song. I've heard this about 100.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, chromium, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, and magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
What do you think about that? You knew that song. You heard that song before?
No, but it's a good song.
Now, I'm not going to play all these, but this, do you know this guy?
No.
Have you ever heard of this guy?
Yeah.
You know him though?
Isn't he Harry Potter? Yeah.
He actually was on a talk show, and he actually sings it, but you probably don't want to hear him sing
I
it.
do want to hear him.
Huh?
I really want
Do you know him?
Yeah.
Okay, all right. You want to do that?
Give a big shout if you know who Tom Lehrer is.
Tom Lehrer wrote this song around 1950.
Okay, so Tom Lehrer, in my opinion, is the cleverest and funniest man of the 20th century, and he's kind of my hero. And he wrote a song called The Elements, because he was a scientist, and it's the name of every element in the periodic table. And that's my last thing. It's quite long, so do stop me if you just get bored.
Okay.
But I will. This kept me up last night. I was so nervous about doing this.
Do I feel bad now?
No.
Okay, so.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and uranium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, anthium, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, and iridium, and strontium, and silicon, silver, and samarium, bismuth, chromium, lithium, iridium, and barium. And let's start the next verse. There's holmium, and helium, and hafnium, and erbium, phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium. There's lead, praseodymium, platinum, plutonium, palladium, lithium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, radon, neon, zinc, and argon. Hold on, quiet. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, radon, neon, krypton, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium.
Oh, wait a minute. Anyway, like I said, you can watch them. There's this guy from Big Bang Theory. He did it. There's a whole bunch of them. There's some. One of I didn't show you this one. One of them, they took some Lego characters and made a like a claymation out of Lego characters.
Oh, yeah, can we do that?
So,
Can we do that?
and this right here is the. This is the new one. I don't know if you.
Oh yeah, let's hear it.
Let me see how long this is.
It's probably like 4 minutes.
If it's too long, I don't think I'm gonna do it. But
It's got 27 minutes.
3 minutes. It's
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, and oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the sign, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
phosphorus, and sulfur, chlorine, and argon, potassium, and calcium, so you'll grow strong, scandium, titanium, vanadium, and chromium, and manganese. This is the periodic table. No gas is stable. Halogens and alkali react aggressively. Each period will see new outer shells where electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel, points again, copper, zinc, and gallium, germanium, and arsenic, selenium, and rhodium, and krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silverware, then cadmium and indium, tin cans, antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, chromium, erbium, thulium, and terbium, lutetium. Hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead that is good for your tummy, polonium, astatine would not be yummy, radon, and cesium will last a little time, radium, then actinize at 89. This is the periodic table. Noble gas is stable. Halogens and alkali react aggressively. Each period will see new outer shells where electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, fermium, indolenium, nobelium, lawrencium, rutherfordium, deuterium, spherium, bohrium, necesium, neodymium, neptunium, mercurium, copernicium, bihonium, flerovium, moscovium, livermorium, tennessine, and oganesson, and then we're done.
That's pretty good.
Thank you guys so much.
They
for
went all the way
watching.
to
If you like the
118.
song, make sure you check it out on iTunes.
They went all the way to 118.
If you think you'd enjoy other videos like this, make sure
I only know the-
All right. So anyway, now.
Muscle science.
Oh no, I know you do muscle. Anyway, I think that song would be harder to learn than this one. So if anybody's thinking about it, but let me know anytime this quarter. If you do it anytime this quarter, just say I'm ready to do it in front of the class, and okay, I'll do that for you. All right. Now the next thing we're going to do is I'm going to kind of gear up for our first test, and I will tell you that you already had a test on the elements, so. The first test covers chapter 1, and I'll be giving that back to you. I already graded all that, homework, and there are about 8 questions on that, and you won't have a test until probably a week from Friday. But the bulk of the test has to do with the candle. Now, right now, you guys discovered things about the candle, but you don't know for sure about things, do you?
No.
So what we do is, I'm not supposed to give any work for the weekend. It's supposed to be a family weekend. But starting Monday, I have a packet for you, and we will start going through the packet in class, okay? And you can take it home, and I write little notes on there. But what I'd like to do, before we do it today, I knew we were going to be a little short on time today. So what I want to do is show you one more video. And one more video, there's a guy, and he took Faraday's... He did these lectures, Christmas lectures for juveniles, for teenagers. And he brought them into the Royal Institute, and he actually set up all these demonstrations. But this guy is going to do some of the demonstrations, but he's going to read word for word some of Faraday's actual words when he gave the thing. Now, I'm sure Faraday paused and stuff like this. This guy's trying to make sure it's... so I want to show you part 1 of this. And then what we'll do is, on Monday, we will read an article where a real scientist went through and tried to study a candle with modern equipment. And we're going to figure out how the candle works, okay? All right, so one more. I think it's still here. There it is. And, all right. This is part 1. I think it is. It should be part 1. Yes. He's reading the actual words that Faraday used.
I will tell you in 5 lectures the chemical history of a candle. There is not a law under which any part of the universe is governed which does not come into play and is touched upon in the chemistry of a candle. There is no better, there is no more open door by which you can enter into the study of science than by considering the physical phenomena of a candle. I trust, therefore, I shall not disappoint you in choosing this for my subject rather than any newer topic, which could not be better were it even so good. So, now as to the light of the candle. Notice that when the flame runs down the wick to the wax, it gets extinguished, but it goes on burning in the part above. Now, I have no doubt you will ask, how is it that the wax, which will not burn of itself, gets up to the top of the wick where it will burn? We shall presently examine that, but there is a much more wonderful thing about the burning of a candle than this. You have here a solid substance, the fuel, with no vessel to contain it. And how is it that this can get up to the place where the flame is? How is it that this solid gets there, it not being a fluid? Or when it's made of fluid, then how is it that it keeps together? This is a wonderful thing about a candle. You see that a beautiful cup is formed. As the air comes to the candle, it moves upwards by the force of current which the heat of the candle produces. And it so cools all the sides of the wax as to keep the edge much cooler than the part within. The part within melts by the flame that runs down the wick as far as it can go before it's extinguished, but the part on the outside does not melt. The same force of gravity which holds worlds together holds this fluid in a horizontal position, and if the cup be not horizontal, of course the fluid will run away in guttering. You see, therefore, that the cup is formed by this beautifully, regularly ascending current of air playing upon all sides, which keeps the exterior of the candle cool. No fuel would serve for a candle which has not the property of giving this cup. These beautiful candles, which are irregular and intermittent in their shape, cannot have that nicely formed edge to the cup, which is the great beauty in a candle. I hope you will now see that the perfection of a process, that is its utility, is the better point of beauty about it. It is not the best looking thing, but the best acting thing, which is the most advantageous to us. These good-looking candles are bad burning ones. There is guttering because of the irregularity of the stream of air and the badness of the cup which is formed thereby. You may see some pretty examples, and I trust you will notice these instances of the action of the ascending current when you have a little gutter running down the side of a candle, making it thicker there than it is elsewhere. As the candle goes on burning, it keeps its place and forms a little pillar sticking up by the side because as it rises above the rest of the fuel or wax, the air gets better around it and it is more cooled and better able to resist the action of the heat at a little distance. Now, the great mistakes and faults with regard to candles, as in many other things, often brings with them instruction which we should not receive if they had not occurred. We come here to be scientists, and I hope you will always remember that whenever a result happens, especially if it be new, you should say, what is the cause? Why does it occur? And you will in the course of time find out the reason. Then there's another point about these candles which will answer a question, that is, as to the way in which the fluid gets out of the cup, up the wick, and into the place of combustion. You see that the flames on these burning wicks do not run down to the wax and melt it all away, but keep to their own right place. They are fenced off from the fluid below and do not encroach on the cup at the sides. I cannot imagine a more beautiful example than the condition of adjustment under which a candle makes one part subserve to the other to the very end of its action. A combustible thing like that, burning away gradually, never being intruded upon by the flame, is a very beautiful sight, especially when you come to learn what a vigorous thing flame is, what power it has of destroying the wax itself when it gets hold of it, and of disturbing its proper form if it comes only too near. But how does the flame get a hold of the fuel? Capillary action conveys the fuel to the part where combustion goes on, and it is deposited there, not in a careless way, but very beautifully, in the very midst of the center of action which takes place around it. Now, I'm going to give you 2 instances of capillary action. It is that kind of action or attraction which makes 2 things that do not dissolve in each other still hold together. When you wash your hands, you take a towel to wipe off the water, and it is by that kind of wetting or that kind of attraction which makes the towel become wet with water that the wick is made wet with the wax. If you throw the towel over the side of the basin, before long it will draw the water out of the basin like the wick draws the wax out of the candle. Let me show you another application of the same principle. You see this hollow glass tube filled with table salt. I'll fill the dish with some alcohol colored with red food coloring. You see the fluid rising through the salt, There being no pores in the glass, the fluid cannot go in that direction, but must pass through its length. Already the fluid is at the top of the tube. Now I can light it and make it serve as a candle.
What do you think about that?
The fluid has arisen by the capillary action of the salt, just as it does through the wick in the candle. Now, the only reason why the candle does not burn all down the sides of the wick is that the melted wax extinguishes the flame. You know that a candle, if turned upside down so as to allow the fuel to run upon the wick, will be put out. The reason is that the flame has not had time to make the fuel hot enough to burn as it does above, where it is carried in small quantities into the wick and has all the effect of the heat exercised upon it. There's another condition which you must learn as regards the candle, without which you would not be able fully to understand the science of it, and that is the vaporous condition of the fuel. In order that you may understand that, let me show you a very pretty experiment. If you blow a candle out carefully, you'll see the vapor rise from it. You have, I know, often smelt the vapor of a blown out candle, and a very bad smell it is. But if you blow it out lightly, you'll be able to see pretty well the vapor into which this solid matter is transformed. When I hold a lighted match 2 or 3 inches from the wick, you can observe a train of fire going through the air till it reaches the candle. I'm obliged to be quick and ready, because if I allow the vapor time to cool, it becomes condensed into a liquid or solid, or the stream of combustible matter gets disturbed. Now, to the shape or form of the flame. It concerns us much to know about the condition which the matter of the candle finally assumes at the top of the wick, where you have such beauty and brightness as nothing but combustion or flame can produce. You have the glittering beauty of gold and silver, and the still higher luster of jewels like the ruby and diamond. But none of these rival the brilliancy and beauty of flame. What diamond can shine like flame? It owes its luster at nighttime to the very flame shining upon it. The flame shines in darkness, but the light which the diamond has is as nothing until the flame shine upon it when it is brilliant again. The candle alone shines by itself and for those who have arranged the materials. The flame is a bright oblong, brighter at the top than toward the bottom.
All right. I'm gonna stop because class is over. So have a good 3-day weekend, and don't forget your schedule changed for today after lunch.